Welcome back, Virtual Physical Science. This week we're going to learn about something called electromagnetism. Now you can look at that word and see that it's going to be about electricity and about magnetism. In fact, it's about how electricity and magnetism relate to and cause each other. Because although electricity and magnetism are two different forces, they're very strongly related. And the relationships between them can be exploited to make lots of modern-day gadgets and explain how lots of things around us work. This is one of my favorite units all year. In this lecture, we're going to learn about how an electromagnet works, what makes speakers work, an electric motor, and different kinds of gauges. All right, it all began back in the 1800s when a Danish physics teacher named Ørsted, made an accidental discovery. He was doing a demonstration with electricity, passing a current, a pretty large current, through a wire, stopping the current and then passing it back the other way, etc. And he just happened to notice that there was a compass, a magnetized compass for telling which way is north, laying next to the wire that had the current in it. And when he turned the current on, he saw the compass needle move. And when he turned it off, he saw it move. When he turned it on going the other way, he saw the compass needle move the other way. So he made a hypothesis. Ørsted said, now wait a minute, electricity and magnetism are different things. But it seems like when I put an electrical current through this wire, this magnet is affected. So he hypothesized that an electric current produces a magnetic field of its own, and that the magnetic field produced by this electric current is what was causing that compass needle to deflect. And it turned out that he was right. Electric currents really do produce magnetic fields. An electric current producing a magnetic field and a magnetic force. Pretty cool. These arrows in red represent the direction of a current. So electrons would be moving the other way. And these circular green arrows represent the magnetic field. It turns out that a current produces a magnetic field that's arranged in a circle around the wire. And a current going to the right would produce a magnetic field as drawn in the top diagram, and a current to the left would produce a magnetic field circling in the opposite direction as shown in the bottom diagram. To figure out which direction the magnetic field would go, take your right hand, it only works for your right hand, not your left hand, and point your right thumb in the direction of the current, and then you curl your fingers in the natural way, and they will curl in the direction that the magnetic field will be produced. So this is called the first right-hand rule of electromagnetism. So all currents produce magnetic fields. And once this was discovered, people invented some pretty clever tricks for increasing the strength of that magnetic field and putting it to different uses. The first trick is to coil the wire. Make the wire into loops, like the red loops in the top diagram here. Where the wire is straight, the magnetic field is curled around like we discussed. But where the wire is curled around, it turns out that the magnetic field is more straight, and it's increased in strength. It's all bunched together inside that coil. The next trick is to put a piece of iron inside those coils. Because iron has the potential to have its domains all aligned, when the magnetic field inside the coils of wire causes that to happen in the iron, that magnetic field is strengthened and amplified even more. So a coil of wire wrapped around an iron core with current running through it is called an electromagnet. One obvious thing that electromagnets are good for is picking up metal. This thing that's hanging from the chain is an electromagnet. The wire that's dangling off the front is sending a current to coils that run around a piece of soft iron inside. When the current is switched on, the thing becomes highly magnetic and can pick up these heavy pieces of steel junk. When the current is switched off, it's no longer a magnet and the junk falls off. They use soft iron because the domains in soft iron are easy to align and unalign on command with the flick of a switch as the current is switched on and off. So an electromagnet can be used to lift heavy junk like this around. But what else is it good for? Well, it turns out that an electromagnet is the key element in speakers. Because magnets push and pull on other magnets, and electromagnets do too, and because we can control the current in an electromagnet, what we can do is we can control that push and pull however we like by changing the current. A speaker starts out with a piece of iron or other magnetic metal that has a coil of wire wrapped around it. That coil of wire is attached to whatever the source of the music or the sound is. That could be your iPod, your stereo, your computer, etc. And that source of sound, what it's going to do is it's going to send electrical signals that correspond to the musical pattern that you're hearing. And those electrical signals are going to be changes in current that pass through the coil around this piece of metal here. And as that current changes, because the music changes, the magnetic field produced in this electromagnet is going to change. Now, if we put another magnet, what's called a permanent magnet, just a normal magnet, next to that electromagnet, then as the current in the electromagnet changes and the magnetic field produced by the electromagnet changes, well, the permanent magnet is going to push or pull on it in different amounts, right? If the current going to our electromagnet is very small, then the permanent magnet is only going to push on it a little bit. If it's very large, then the permanent magnet is going to push on it a lot. If the current goes the other way, then the electromagnet is going to pull on it the other way. And if we make all sorts of really complicated and rapidly changing patterns of current flow through the wire around the electromagnet, then it's going to make all sorts of rapidly changing and complicated motions. The final ingredient in the speaker is some kind of thin membrane or cardboard cone that's attached to this electromagnet and that shakes along with it. In your headphones for your iPod, the membrane is actually a very thin membrane of plastic. If you open up an old pair of headphones, you can see these things. In larger speakers, it's either a piece of a very thin, flexible metal or actually cardboard. And as that membrane or cardboard cone shakes, it causes vibrations in the air, which, as we know, are sound waves. These sound waves will be at the right frequency and amplitude because the current oscillations in the electromagnet were at the right frequency and amplitude. These sound waves will travel across the room and come to our ears, and we'll be delighted and thrilled by the music coming out of the iPod. So it's a brilliant and wonderful transformation of energy, from electrical energy to kinetic energy to sound wave energy. Another thing that electromagnets are really important and useful for are something called galvanometers. Now, you may have never heard of this word before, but I bet you've seen a galvanometer in action. It's pretty similar to the speaker. It works by first having an electromagnet, that's this wheel here in the middle. It's just a piece of metal with wire coiled around it, and we'll pass a current through that, and we'll talk more about where that current comes from in just a minute. And because that electromagnet wheel is next to a permanent magnet, which is shown in green here, well, when the current flows through it and it becomes a magnet, it will push on and pull on that permanent magnet and it will start to move. And this wheel will be free to rotate. That's what I've tried to draw on here with this axle. And so if the current in this electromagnet changes, then the wheel will actually rotate. And this is the basic idea of a galvanometer. So if we attach a little indicator arrow to the top of our galvanometer, then we can use it to measure different kinds of things. For example, in your gas tank in your car, there's a sensor that determines how high the level of the gas is, the petrol, and the higher it is, the more current it produces. It sends that current to a galvanometer, and that galvanometer will turn more or less depending on how much fuel is in the tank. And you can read that off of the scale that goes between empty and full. There's also a little spring in place that resists the turning of the wheel so that the current is necessary to produce any kind of deflection of the needle. This could also be used for a temperature gauge or any other kind of gauge you can think of in a car or in some other kind of measuring equipment. So galvanometers are another really useful application of the relationship between electricity and magnetism. The final and perhaps most useful one of all is an electric motor, but we're going to have to get to that in part 2 of this section. See you there.